All right, today we're going to finish up chapter 4. The next two sections are pretty straightforward, quick and easy. I hope. The first one, section 2, deals with the addition and multiplication rule. I talked a little bit about this on Monday. At the very end of class, I told you what we're going to talk about in the addition and multiplication rules. So the addition rule deals with the sum of two probabilities. We use the word or to mean addition. And this is how we represent it, the addition rule. And we'll get to the formula for this. So this is read: the probability of event A or event B happening together or individually. The multiplication rule deals with the probability that two events where one event can affect the second event occurrence. In other words, one event has an influence on the other. We use the word and. And that's the probability would be stated. Remember what a simple event was? Review from section 1. A simple event is an event that cannot be broken down into any further event or events. For example, you have one coin, you flip it, that's a simple event because nothing else can happen. It's either going to be a head or tail. That's a simple event. Compound, which is what we're going to deal with this chapter, this section. A compound event an event consisting of two or more simple events. So what does that mean? An example of a compound event would be rolling two die. Because a simple event is one die. This is two dice. Because when you roll two dice, how many ways can you roll a 3? You can have a 1 and a 2 being rolled, or a 2 and a 1. Because remember, they're separate events. So the first one you roll is a 1, the other one's a 2. Or the first one's a 2, and the other one's 1. As long as the sum of those equals 3, that means it's a compound event. You can have multiple simple events that make up them. Right. So in other words, that's what we're gonna look at. We're gonna look at how many different ways can an event occur. That's what we did that two dice. We had 36 possibilities. Let's first define the addition rule. PA or B. It's the probability in a single trial or event A occurs or event B occurs or they both occur. So it's the probability that in a single trial, event A, that's what this says, event A or event B occur, or they both occur. Intuitively, what does this mean? Probability of A or B means this. The number of ways A can occur plus the number of ways B can occur remember, or is addition, but but in a way that an event can only be counted once. And then you divide by the total number of outcomes possible in the sample space. Remember, what is a sample space? The total number of possible events. Yeah, all possible event combination of events. That's a sample space. But this defines a probability. Remember, a probability is the number of times X occurs divided by the total number of outcomes possible. That by definition is how we calculate the probability of something happening. Okay, so now here's the algebraic. Algebraically, the probability of A or B so in our intuitive way, it says the number of ways A can occur, number of ways B can occur, but only once divided by that. So we're looking at probabilities. So this is going to be the probability of A plus the probability of B can A and B share the same outcomes? They don't have to, but they can. In other words, remember I said the example I used last time is if I had a deck of cards, and what is the chance of me pulling out a red card or a 10? Can you have a red 10? Yeah. So this is where you have to subtract. Where they're the same. So let's look at the example of a deck of cards. Probability of choosing a red card or a 10. From a standard deck of cards. I forgot about that last part. It's very important. Why? Because are all decks of cards the same? No, because if you ever played bridge or pinochle, cards are different. You don't have face cards. But if you have a standard deck of cards, the standard deck of cards goes from 2 to 10, Jack, Queen, King, and Ace. There are 13 cards. Then you have 4 suits. You have diamonds, hearts, clubs, and spades. So 13 times 4 is 52. There are 52 cards. So what this thing says here is asking us to find the probability of a red card or a 10. So this is event A, this is event B. The probability of event A plus the probability of event B minus the probability of a red 10. Can these two, that's what you have to look at. Sometimes it doesn't. Sometimes they can't overlap. Then it's 0. But if it can overlap, look at, can you have, the question you have to ask yourself, can you have a red 10? Yes. So we have to look at how many red cards are there in a deck of cards? Yeah. So there's 26 out of 52. How many 10s are there? Yeah, 1 in each suit. So it's 4 out of 52. How many red 10s are there? So you have the possible outcomes over the total number of outcomes. Possible outcomes of this over that. Since you have the same denominator, we combine the numbers. 26 plus 4 is 30 minus 2, 28 over 52. And of course, you're supposed to simplify it, but this relates better to a deck of cards. If I drew 52 times, I would get a red card or a 10. That's on the average. Remember the laws of large numbers. And if we simplified this, we get 14 over 26, 7 over 13. Which means if we drew 13 cards out of a deck, 7 of them would either be red or 10s. We could get all of them. Our first couple of times, we get all of them to be red 10s or red cards or 10 cards. Other times we get none of them. So this is after 100,000, a million trials. This is what's going to be the standard average of Law's numbers. So far, so good. So we have to look at, so now let's look at examples of charts, using charts. Drug testing of job applicants. Using the table below, if one subject, why do I use subject? Because it refers to people. So when you refer to people, you talk about subjects. If one person is randomly selected from 555 people and given a drug test, find the probability of selecting a person with a positive test result or uses drugs. So we're looking at positive result or is a user. So what do we have to do first? Do we know how many we have total? It says 555. So let's see where those 555 come from. If we add these two together, what does that give us? 45 plus 5 makes it 50. 25 plus 480 makes it 505. Add those together, we get 555. Or if we go up and down, 45 plus 25 is 70. 480 plus 5 is 485. 45 plus 70 is 55. We have to first, that's your first checks and balance. You have to make sure that works, because if it doesn't work, then we can't go any further. Because that means you had something wrong with your data set. So the probability of testing positive plus the probability of being a user minus the probability of testing positive and being a user. So what's the probability of being a positive on a test? Positive test result is 70. So that's 70 out of 555 people. What's the probability of being a user? Uses drugs. So you add these two. So it's 50 over 555. Now, where do those two lines overlap? Remember, the first one we used was this one, and then we used this one. All right, so they overlap here. So that's so now we combine all those. 70 plus 50 minus 45. $50 minus 45 is 5. So the answer is 75 out of 555. So the probability of testing positive or as a user is 75 over 555, or 13.5%. That's your probability of getting one. So this is how you look at your charts and put them together. Any questions? Yeah, you have to be very careful. Like when it asks you these things, the first says positive test result. So out of all these, you look at which one tests positive. That's this one. So you add up all those. Then which ones are users? Which one of these says users? There's users drugs. So you have to add up all those. And then anywhere they overlap, anywhere these overlap, you subtract that because you counted that number twice. Okay. Disjoint events. And the addition rule. What does disjoint mean? Yeah, so yeah. If your knee is disjoint, what happens? You can't use it. Disjoint means when two events cannot occur simultaneously. Or cannot happen together. So if your knee's disjoint, the top part and the bottom part cannot work together. It just, if your shoulder is disconnected, same thing there, it just dangles there. You can't do anything with it. Why is this lucky for us? Yeah. If in our addition rule, if two things cannot occur at the same time, there's no overlapping, is there? So this part is gone. This part, it becomes 0. So our formula now becomes the probability of A or B is simply the probability of A plus the probability of B. Since they cannot occur together at the same time, they're disjoint. We also call that mutually exclusive. They cannot overlap. Here's the example here. You have disjoint events. What does disjoint mean? They cannot occur at the same time. So here's someone. Event A is randomly selecting someone for a clinical trial who is male. Event B, picking one that's female. Can you have, I don't care what people say, it's either male or female. I don't care what they choose to be. So there's the overlapping part, there's no overlapping, cannot be both. So the probability is simply probability of A, probability of B. So the probability of being male plus the probability of being female. If they're not disjoint, meaning they can occur together, someone who's taking a statistics course, event B, someone who is female. Can a female take a statistics course? Yeah, so those overlap. So we have here the probability of stats plus the probability of female minus the probability of female in a stats course. Because you counted them here and you counted them here. Those are examples of what mutually exclusive really means. Go back over here. So let's summarize. Of the addition rule. We use the word or in the problem. We remove any overlapping events. So far, so good. Let's talk about this property now. Complementary events and the addition rule. Last time we talked about at the end of class on Monday, what does complementary mean? No. Complementary means the opposite of what is being examined. That's one way you say it. The symbol we use, remember, A is for an event. It's red, not A. So here's an example. If our data set consists of 1, 2, 3, 4, 5, 6, 7, 8, numbers 1 to 8, and A equals 2, 3, 5, 7, what would the complement of A be? Because this is our data set. It's got to be in brackets. Right. So basically what it really means is, here's our data set. cross out these. Cross out 2, 3, 5, and 7. Whatever's left is the complement. 1, 4, 6, 8. The example I used last time. When rolling 2 dice, what is the probability of rolling a number less than 10? Okay, now let's recall this. We have 2 dice. The smallest you can get is a 2 less than 10. So this could be 1 and 1, 1, 2. Remember, these are 2 separate dice. The first one's dice A, that's what, so it's 1, 3, 2, 2, 3, 1, 1, 4, 2, 3, 3, 2, 4, 1, 1, 5, 2, 4, 3, 3, 4, 2, 5, 1, 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. You notice how one side goes up, the other side goes down. So since there's no 7, we have a 2, 6, 3, 5, 4, 4, 5, 3, 6, 2, 3, 6, 4, 5, 5, 4, 6, 3, 4, 6, 5, 5, 6, 4, 5, 6, 6, 5, and 6, 6. Since each die has 6 sides, 6 times 6 equals 36. There's 36 possibilities. There's 36 numbers. We're looking for what's the probability of rolling a number less than 10. So that's all of these. You could count all these. Takeaways, exactly. Takeaways you don't need. We don't need these 6. So 36 minus 6 equals 30. So 30 over 36 are the numbers less than 10. Gotta fix this thing from swaying so much. That's the complement. Because since we're looking for this, we don't want these. So the complement is, it's easier to find the complement of A. The probability of not finding less than, but 10 or greater. Or greater, which is smaller. So how do they relate to each other now? We know this. The summation of all events, the probability of all events has to equal 1 or 100%. Remember, probabilities have to be between 0 and 1. Meaning they're decimals. If we add up all our decimals, it has to equal 1. Example. One die. What are the possible outcomes if you have a die? If you roll one die. 1, 2, 3, 4, 5, 6, right? So the probability of getting this is 1 over 6, 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 1 over 6. Because they each have a 1 out of 6 chance of being chosen. If I add up all of these, I have a common denominator. How many ones do I have? And 1 over 6, that's a decimal. If it's less than 1, greater than 0, that satisfies this condition. And if I add them all up, I get a 1. So that's how you can tell if your numbers and your example is correct. If you add them all up and it's bigger than 1, you can't use it. Because you cannot have more than 100%. Because 1 equals this. Remember, this is 1.0. 1.0 into percent is 100%. So again, we cannot have more than 100%. So what that says is the probability of an event plus the probability of its complement has to equal 1. Does it work with our 1 die? Let's say, what's the probability of rolling a 2? That's 1 over 6, right? So that's 1 over 6. And we don't want what the other ones, which are 5 over 6. Add those together, we get 1 over 1. Okay, now this one, we can now look at different ways. If we're looking for our answer, or if we're trying to find the complement, we can use all of these to mean the same thing, to find the same answer. Because we used this one earlier with those 2 dice being tossed. We had 1 minus how many we don't need? We don't need the 6, so we're left with 30 over 52. No, 30 over 36. All right, let's look at an example here. Sleepwalking. Based on a journal article by Ogham et al., prevalence and comorbidity of nocturnal wandering. Nocturnal means nighttime. Morbidity means death, comorbidity. In the US, general population, Neurology, volume 6. The probability of randomly selecting someone who has sleptwalk is 0.292 or 29.2%. If a person is selected at random, what is the probability of getting someone who has not slept walked? Yeah, we want somebody who has not slept walked. So that's 1 minus the probability who has slept walked. 1 minus 0.292 is going to be 0.708. Or 70.8% chance of picking somebody who has not slept walked. I have no. I've known people who have slept walked, and it's so scary. It's so weird. It's. I mean, their eyes are open. They're walking around, and you heard that if you wake them up, they'll get lockjaw, but you always want to just see what you can get away with. Yeah, but no, it's just so weird. It's like somebody who's a zombie. And they don't remember any of it. Do you remember it? It's like a dream then. That's weird. Yeah, the mind is such a amazing thing. Now let's talk about multiplication. The multiplication rule. This one gets a little bit more complex. A and B. With this way, the way we would write this as a probability is the probability of A occurring and the probability B occurring we now introduce this symbol. This one says the probability of event B occurring given that event A has occurred. George, event B occurs after event A. So it has two meanings. In multiplication, event A and event B occur in different trials. Or they occur in the same trial. What's the difference? Why would it make a difference? Well, give me an example of they happen in different trials. That they won't matter. Yeah. So cards and dice or coins and cards. Yeah. Where two separate trials, two separate events where one does not influence the other at all. But if they happen at the same time, then we can now have a problem because if I have a deck of cards and I keep the card or I put it back, and that changes the probabilities of one to the other. But again, the first event has to happen before the second event even tries. Okay. And this is what it looks like. Equals the probability of A times the probability of B given A. That's how you read the second one. Probability of B given A. That's what it means. In other words, A has to happen first before B even, because if you have a conditional probability that says A and B have to occur, A has to happen first before B gets started. For example, you have two more classes to graduate. Calculus 1, Calculus 2. Can you graduate if you fail one and pass the second? No, because you can't take the second if you don't pass. So it's conditional that you pass the first and then you pass the second. All right, so here we're going to look at what are called independent events. And the multiplication rule. What does it mean to be independent? Hmm? Yeah. Independent mean does not affect the other. So the occurrence of one event does not influence or affect the occurrence of the second event. That's what independent means. What do you think dependent means? It simply means not independent. That's how you'd find it in most math books. If it's dependent, that means it's not independent. So for us in this class, we will use with replacement. And without replacement. With replacement means after event A is completed, the object is returned before event B starts. I wish I could use y'all's handwriting because you see mine's horrible. So now we're talking about dependent versus independent. Is with replacement dependent or independent? Relating with replacement, relate it back to, is it dependent or independent? An event that happens with replacement, does that define an independent or dependent event? Ooh, we have two people and two different answers. Think about it. Independent means what? The two events don't influence each other. So if I put it back, does the first one influence the other? No, because it's the same as if I did the second example first. So this is independent. Meaning the first event does not influence the second. Yeah, but with. Yes, you're right. That means, right. That means, right. No. So without replacement, you keep the results of event A before event B. This is dependent because event A will influence the odds for event B. Selecting two cards from a deck. And getting a king and a 5. So the probability of a king and a 5. The probability of a king and a 5. So this seems the probability of a king times the probability of a 5. Everything looks the same until we get to this part. What's the probability of getting a king with replacement? There are 4 kings in a deck of cards out of 52 cards. You put the card back, you get a king on the first draw. You put the card back. What's probably getting a 5 on the second draw? So it's 16 over. Yeah, whenever you multiply fractions, you multiply top by top, bottom by bottom. You only keep the bottom the same when you're adding and subtracting. Because think of this. If I said king or 5, I now have a easier chance of getting those two. This is more complex because I have 4 cards out of 52. I have to get that one first. And then when I put it back, I have 52 more cards again. So I now have a much smaller chance of getting it. The probability of getting a king in the second without replacement, 4 out of 52. And you keep that king. What's probably getting a 5? 4, 51. Because I kept the king. I have 1 card less in the deck. The odds have gotten a little bit in my favor because there's 1 less card to have to worry about. The fewer cards you get, the better your chances. Think about the lottery now. How many numbers are there can you choose from in a lottery? No, it's like 40. Yes. Well, but you have different in a lottery you pick, but you have a bubble sheet. You have to pick 1 through, actually 0 through, let's just say 20. Let's say, but something like 46, 50 numbers, some big number like that, some weird number. So let's say you pick a number between 0 and 20. How many numbers is that? 21 numbers. So you have to get 6 of them correct. And then if you want to do the jackpot, you have to get an alphabet letter, A through Z, which is how many? 26. You say 23. Okay. 27, it's even worse. Oh yeah, the Hispanic alphabet has more. Yeah. So we have 21 chances here, 21 here, 21 here, 21 here, 21 here, 21 here. It has to be multiplied because in order to win, you have to get the first one right. And you have to get the second one right. And the third. And so it's all multiplied. And if you want to do the jackpot, you have to do that one. So you have to do all those together. And you only have 1 chance each time you play. You have 1 out of all those. Yeah, it's some what's the number you get? So it's 21 to the 6th power times 26. No, that sounds very small. Let me see.
Yeah, okay, got it.
Okay,
Yeah, I'll just give you the numbers.
okay, okay.
It's 2, 2, 2, 9, 9, 1, 9, 1, 4, 6. Okay,
It's 2,229,919,146 to one chance. That's if there's 21 numbers in there. So it all depends. If it's 1 through 10, it's a little bit easier. It's smaller, but you're still looking at huge numbers.
But those, when people pay huge amounts of money, right?
Yeah, well, people normally play it, but people play it all the time. Some people play it every week. Like my parents, whenever they got gasoline, they'd go in there and buy 5 quick picks.
Well, which was the one that they come out of the road and-
Well, like Powerball, but people, that only comes in the news. People see, here's the thing about it. People will win 5 or 6 or $15 million all the time. But recently it was like 1.01 or 04 billion dollars. That's when it becomes news because it makes now you're an instant billionaire. After actors, you still come up with like 600, $700 million.
It's still some, it's, they take away the number. I think, well, my thing is that, isn't that the same thing like with the numbers?
Yeah.
How do they get that money? Like from the people that always play?
Yeah, the jackpot is because of it's based on number of people play. So let's say that the 3 of us played and we each paid $30 or $10 a piece. We'd pay $30. They will give out $22 as a jackpot because they're going to make money no matter what. The house always makes money. So if it's a $1.1 billion, you know that the state is making a crap load from what people are buying. Plus, they'll take the taxes 47% off the top when they hit it. And then, not only that, but they also have to pay out the money to the gas station or wherever they bought the ticket. They get like 10%. Yeah. It's just so convoluted. Same thing happens. Yes. I remember one time I went in Shreveport. I won $4,600 jackpot on one hand of cards. And it was so weird. They stopped the game. They put police on 3 corners and they told everybody else to leave. They told me I couldn't leave, I couldn't move. They were watching the videos, make sure I didn't cheat. They took my fingerprints, they did everything to make sure everything's they took the cards, they had to examine all the cards, make sure that they're still legitimate. I mean, I was there for about an hour waiting to get my money. And then they took me to the back, they gave me a check. Well, they asked me if I wanted cash or a check. I thought I'll put it in my bank account. And they gave me a suite for the night and free food. They want to keep me there for as long as they could to get the money back.
Oh, yeah.
And you know, as I said the last time, is the law of averages is the house will always win.
Well, I feel like for people that have casinos, I think they always have people watching all the.
Oh God, it's the most secure places in the world. They have IA securities everywhere, infrared, geothermal, the thermal imaging. They'll see if you have anything on your body. The chips themselves have sensors and magnet stuff in there, where they can tell exactly where it is and how many chips there are. So yeah, it's a big business. It's this example. Yeah, it's amazing. But you know what I've learned about casinos, there are no windows in a casino.
They have like these little fake windows that have like light, but once you walk out, it's like pitch.
It's you're there all night. There are no clocks, so you don't know what time it is. The air quality, they inject oxygen in there every certain number, so it keeps your body, because the more oxygen you have, the more awake you become. So that's gonna be, you don't realize how long you've been there betting and gambling. I forgot what it is. Yeah, we're supposed to, but we bring mostly carbon dioxide. All casinos. All casinos. Yeah, but now they're doing, you don't smell that many smoke anymore because they took away, oh, you can't smoke near the machines anymore at games. A lot of them are smoke free now. So yeah, it's pretty high tech. It's as high tech as you can get. It used to be that people up in the attic looking at people with binoculars and stuff, but no, they have imaging, they have X-rays coming in when as soon as you walk in there, they look at your body, your face to see if it matches any picture on their black book, to see if you're not supposed to be there. Yeah, it's pretty high tech. Anyway, let's look at this example. Using the 50 test results from a drug test subjects as shown below. Positive test results 45, negative. If 2 of these 50 subjects who used drugs randomly selected with replacement, find the probability that the first selected person was a positive test result and the second person was a negative test. So what we're looking for is a positive in the first one times a negative given the first one was positive. So how do we set this up? So how many positives are there? We're looking at if 2 of these. The positive test results are 45 over 50. And the second one? Because we're saying, okay, the first one is positive test, good. So what would be the chance of the second one? How many negatives are there? And let's see what the numbers give us. Which that would give us approximately 0.09 or a 9% chance. Okay, repeat part A now without replacement. So the probability of the first one being positive and the second one being negative. Times the probability of a negative given the first one was a positive. So what's the second part going to be? No, it can't be. Five over 49. Then you do the multiplication there, and there you have it.
So every time we do the second part, you remove one?
If it's without replacement, right?
Okay.
This is with replacement or without replacement. And this is with. So that would be so 0.091. So we'll look at approximately 9.2%. Let's pick another one. %5 guideline for cumbersome calculations. Assume that three adults are randomly selected without replacement from 247 247 million adults in the US. And that 10% of the United States adults in the US use drug. Find the probability that the 3 selected adults all use drugs. How would you set that up? Because now we're using 3 adults. So we have the probability of A and B and C. So what we're looking at here is the probability of A times the probability of B times the probability of C. Those are all we're using without replacement. What do we know for sure? We know that 10% of the US, so we know that this is 10%, this is 10%, and this is 10%. Each adults have constitute 10%, which is 0.1 times 0.1 times 0.1 equals 0.001. What does this number represent? The percent chance all 3 of them use drugs. So 0.001 of what? Yeah, it's 0.001 of this population. So we have 0.001 times 247,436,830. So what's the answer going to give us? Yeah, so we'll move it 1, 2, 3 spaces. Ah, yes, but now we have to look at taking away people. Okay, so it's 10% of this number times 10% of this second number. Right. Times 10% of this number. You know, it's the last number I took away and kept one. So now we have to take these. If it was just, if it was with replacement, then we could have done it the other way, 10 times 10. But this way, it now changes. So remember, we're looking at a probability of each. So this one's going to be 247,436. Yeah, so 10%, we just moved the decimal place over 1. So we got to move the comma over 247,436,830. There's our first probability. This one's going to be 247,436,802.9. But we can't have a 0.9 of person, so we get rid of that. 247-436-830. Right. Two, four, seven, 836, 82. Because these are the probabilities of each one. You get those and multiply them together, and you get the answer. That answer becomes 0.000099999989909. So if you round this, we get that, which is what we said earlier. That's still a lot of drug users. All right. Well, let's look at birthdays. Oh, this is an interesting one. When two different people are randomly selected for from those in your class, find the indicated probability by assuming that birthdays occur on the days of the week with equal frequencies. Or every day of the week has an equal chance of being chosen. There's not one preference. Find the probability that two people are born on the same day of the week. Find the probability that two people are both born on Monday. So we're looking for probability of person A and the probability of person B. So since it's and is multiplication. So the first thing it says is probability of A occurring times the probability of B given that A has already occurred. This is the interesting thing. What is the chance that the people are born on the same day of the week? Because the first person can be born on any day of the week. The one that has to match is the second day, is the second birthday, and it has to match, so its probability is 1/7. Now, they're both born on Monday. So the probability that A was born on Monday and the probability that B is born on a Monday. So what's the probability of A being born on a Monday? One out of 7. What's the probability of B being born on a Monday? Which is 1 out of 49. So the chances are you would have, out of 49 students, one of them would be born on the same day as somebody else. But you see the difference here, because the first one, it said they were both born on the same day of the week. The first one could be any day of the week, so there is no probability there. any day of the week is the day of the week. So the second one has to match that, and the chance of that is 1 out of 7. The second one is more specific. I have to be born on Monday. And the second one has to be born on Monday. Let's see here. Now we're going to get something called redundancy. What is redundancy? Yeah. In computers, redundancy, if you have a redundant system, that means you have 2 of them running in parallel so that if one of them crashes, the other one still works. In the example they have here, the Airbus 310, they have, in the old days, airplanes used to have one set of controls for all the surfaces that move. If those broke, you're dead. Electronics? Oh, solar flares?
I'm not sure if there's. Here. The font, gives a positive charge in the front. Hopefully positive charge. They happen on the election ones. And then also I can bring it home.
Wasn't that, isn't that solar flares causing it? Because the only thing that these sun spits out. And it changes the magnetic frequencies and everything. Yeah, the solar flares are, that's why we need our atmosphere. It protects us from that sort of stuff. But aircraft, they have multiple redundant systems in case one breaks down, there's another one backs it up. Some A310 has 3 of these systems. And A380, even the larger they get, the more redundant the systems become, so that if anything happens, the fuel lines, they have multiple fuel systems. So modern aircrafts are now highly reliable, and one design features contributing to that reliability is the use of redundancy, whereby critical components are duplicated so that if one fails, the other one will still work. For example, the Airbus 310 twin-engine airliner has 3 independent hydraulic systems. So if any one system fails, full flight controls is maintained with another functioning system. Actually, they have 2 of them backing it up. For this example, we will assume that the typical flight, that the probability of hydraulic system failure is 0.002. A, if the Airbus 310 were to have 1 hydraulic system, what is the probability that the aircraft's flight control would work for a flight? And then B, given the Airbus 310 actually has 3 independent hydraulic systems, what is the probability that on a typical flight, control can be maintained with a working hydraulic system? So, Airbus 310, let's look at A. If the Airbus 310 has 1 hydraulic system failing, what is the probability the aircraft flight control would work for the flight? So we're looking at here is what's the probability of working hydraulics? What do we know from the question, from the statement? We know the system failure is 0.02. So if we take, remember, we have the total system working is 1 minus the 0.002, because that's the part that can work. If we take away the part that doesn't work, then we have 0.998. This is the probability that one hydraulic system does not fail. Because the chance of it failing is 0.002. Okay, B. Given that the Airbus A310 actually has three independent hydraulic systems, they're independent. That's important because each one of them occurs separately. So what's the probability of all three of them failing? Which is 0.002 times 0.002 times 0.002. That's going to be 1, 2, 3, 4, 5, 6, 8. One, two, three, 6, 1, 9. 1, 2, 3, 4, 5, 6, 8, 9, 8. So it's point. The chance of all three of them failing is this. So the probability of the Airbus having equals 1 minus 0.000000008, which is 0.999999992.
Now talking about
What's that?
the thing that I was talking about.
Mhm.
They're-
Oh, muons. Yeah. Okay.
That's how.
Protons. Yeah.
That's how. That's what he first said.
I didn't know that.
That's why you're making one? They. Hit the plane. Or hit the computer and it's no slide.
Really?
They were able to just,
Manually,
and then they figured out that we don't fix this.
which is so weird because muon, positron, all those things, those were invented by Star Trek. The terms they used, and then once they discovered it, they said, we'll use that. So yeah, so you see that it's a very, very small chance of a plane nowadays having hydraulic failures. Pretty much same goes with the fuel system because they have multiple fuel lines, fuel pumps that if one fails, they just reroute it. So, graphically representing the tree diagram. A graphical representation of multiple events occurring. For example, What is the probability that you get a head with a flip of a coin and roll a 4 with a die? We could do it algebraically. So we want a head and a 4. Since they're independent events, there's no way they can overlap. We just multiply them this way. What's the probability of flipping a head? 1/2. And getting a 4 out of one roll of a die? So it's 1/12.
Isn't it like yours get heads?
They're equals. They should be equal. That's my cardiologist. Because, yeah, some people say that because the way coins are made, there's more metal on one side than the other. But if you did, again, laws of averages, law of large numbers, it'll come out pretty close. But you're right though. On the head side, there's less metal than the tail side because it has a lot more writing back there. But yeah, we're going on. I'm sorry. Then I should have put here. I should say you have a fair coin and a fair die. Because whenever that has to be stressed just because of that. When a fair die is one that's well balanced and everything. There's no formulas or anything. Because same logic you have there. Because if you think about it, the 6 has more holes than the 1. So it is now lighter than the 1. One's the heavier because it has more surface area. So the people say is you can do that. So it has to be adjusted so that if you look at a die, the center of gravity is right in the top dead center of it. And same with the coin. So, but now let's look at using a tree diagram. You start off, this is what you're looking for. So event 1. What is the first event? Is flipping of a coin. What are your possible outcomes? It can be a head or it can be a tail. Now we look at event 2. This is a coin. This is a die. So from here, after I flip a coin as a head, what can I do when I roll a die? I can get a 1, 2, 3, 4, 5, 6. Likewise, if I roll a tail on the first one, I can roll a 1, a 2, 3, 4, 5, 6. What's that?
Outfits.
What about it?
You have what's called. So we have 3 pants, 2 shirts.
Oh, yes, exactly. Yes, that's exactly. That's the argument men can have against women, saying, "I have nothing to wear." Yes, you do. You will look at that. You have, let's say you had 15 pair of shoes, 5 5 slacks, 10 blouses. That alone gives you 750 different outfits. If you were a guy, it wouldn't matter how you look. But women goes, but you can't wear that color brown or that color tan. It doesn't. So that's really. But yeah, this is how this it's been used. But then also those people who use that have slept outside, are now single.
But I don't know why. Like you put something on, you're like, oh, like it. And then
Exactly.
you throw something on.
And throw something else on.
Yeah, that's things.
I mean, I'm the same way with t-shirts and things. I said, well, this then I got to a point where t-shirt's a t-shirt, shorts are shorts. I don't care what they look like. Okay, so for example, now if we looked at probability of a head and a 4, we can look at first off, there are how many possibilities? There are 12 possibilities and a head and a 4, there's only one of those. A head and a 1, there's one of those, 1 out of 12. Because here are the outcomes possible. There's 1 of 12, 1 of 12, 1 of 12. Each one of these are 1 of 12. And so these. So you can either do it algebraically like this, or if you use a tree diagram, you can see exactly how it goes, which is right. It's or different ways of making a hot dog. You have your wheat or white bread, you have the condiments of each one. So when they said you can have any one of 7,000 meals, what they're talking about here is you can have cold turkey, warm turkey. You can have mashed potatoes. And then you get warm mashed potatoes, cold mashed potatoes, brown gravy, white gravy, and it keeps on going from there. And that does it for this chapter. In this section, we didn't have time to go to the next one. I'll send you a video on that one because that one deals with complements of conditional probabilities. I'll send you the video for that. It's the probability of conditional. Okay, what's probability of this happening if this happens? So yeah, now we kind of touched on it here, but that one there we're going because here in this one our product of our and statement is just this probability times this probability. The next section is we'll look at this probability times this one has to happen if this occurs. So it happens on a condition, which changes the probabilities.
You said, the